So let's say there are 10 different objects, okay? Put into three, let's say 20, right? Put into three boxes. And then the first box should contain 7 objects. The second box should contain let's say 6 8 objects. The third box should contain 5 objects. So how many different ways to put the objects into the boxes? Do you understand the question?
Yeah.
So let me give you 2 minutes to think about this question. And or you can try to give me the answer. The number may be too large. You probably can't use your calculator to find the answer. I'm not sure. So you may just give me the formula. The answer is not 20 factorial because the object can put in different uh, So let me show you the solution, okay? So first one, what you can do is you line up the 20 different objects in a line. Well, here are 7, okay? 8 and 5. So you can put the object one by one. So you can consider there are 20, and then mm, so the first one you can have 20 choices. Second one you can have 19 choices, okay? So it seems 20 factorial, it seems 20 factorial is the answer, but not. Because if you choose, let's say if you label the object as A, B, C, D, E. So let's say I give you let's say it's A, B, C, D, E, okay? But A, B, C, D, E and B, A, C, D, E are the same choice. The order of the objects inside the box doesn't matter. So what you should do what you should do is divide by the given the 7 objects, okay? Given a certain 7 objects inside the box. And then the ordering of the object does not matter. So that means you need to divide by the number of orders of that 7 objects. So you need to divide by 7 factorial. Here you should divide by 8 factorial. And here you should divide by 5 factorial. Okay. Any else and any questions? Any questions? So I'll capture your screen. So let's do another combination question, okay? Actually, some of the textbook may write down this one as in this form to represent this answer. So if no question, and then let's go on to have a look. So can you wait me for 1 or 2 minutes? I'm going to find another question, but I forget the question. I need to have a look. Mm, let me search the problem. Actually, I forget the question already. Let me see, or let me make up the question. So let's say there are, I forget the question already. So, where's the whiteboard? Oh, here, okay. So let me make up another question. So right now there are 10 boxes, okay? Now 5 objects are put into 10 or 9 different boxes. And then one object, each box can only contain one object. So can you find how many different ways to put the object into the boxes? So you try to do it, try to do it. I think the question is this one, yeah. 9p5 times 5 factorial. Oh, I don't think so. No, no, the answer is not that one. This is really a tricky question. It seems the question is not that difficult because you just put 5 objects in 9 different boxes, and each box contains one object. Ah, the objects are identical objects, okay? Identical objects. If they are non-identical, then the question is, I'm not sure if it will be more difficult or not. So the answer is not that easy actually. So maybe let's consider there are, so let's consider the question like this. Can I copy the question? So let's consider the question like this one, okay? Well, let's see how about if there are 5 non-identical objects are put into 9 different boxes, and each box contains one maximum object. So let's see how to do it. So actually, there we use a method we call it ball and stick method. So let me simplify the case, okay? Let's say consider there are 2 balls and then there are 4 boxes. So, and then if there are 4 boxes, we use 3 sticks. So 1, 2, 3, okay? So why we use 3 sticks? Because there are 4 regions. Do you see? Can you see? 1, 2, 3, 4.
Yeah.
And then if the ball is in the first box, then you draw a ball here, okay? that means there's a ball. There is a ball in the first box. If the ball is in the third box, you draw a ball here. That means the ball has in the third box. So and then if there's no ball within two sticks, that means there's no ball inside the box. So if we consider a question like this one, then how can we find the combination? So let's say there are n. So let me generalize the question. Okay, let's say there's n balls. Okay, and then n boxes. If there are n boxes, that means there are n minus one stick. Okay. So the first step, if you draw all the stick first. Eh? I think I mixed up the question. No, yes, no. Yeah, I think I mixed up the question. Sorry, I think I mixed up the question. The ball and stick method is used in another type of question. So maybe let's ignore this part first, okay? So if let's say there are 5 non-identical objects are put into 9 different boxes. So I think it's just the answer should be just the question is just like there are 5, okay? There are 5 different people, okay? 1, 2, 3, 4, 5. And then there are 4 identical objects, and then you are finding the combination to make it in a line. Do you understand what I mean?
Yeah.
So if the box does not contain the object, then and then I just use a black color to represent it. So first of all, if you are queuing up, or let's say if you consider they are a different box, okay, but the box are say different boxes, okay. So you say 6, 7, 8, 9. So if the boxes are different, okay, so there are right now if you line up the 9 objects or 9 boxes or 9 something, okay, you get 9 factorial. And then divide by, if the boxes are identical, how can I say it? So if the boxes are identical, that means you need to divide by 4 factorial. I think that may equal to 9p5. I'm sorry, maybe let me clarify it again, okay? So let me change the question. Let me change the question, okay? Let's say there are n balls, n identical balls. Are put into n boxes.
Which is m larger than n?
Actually, it doesn't matter here.
Okay.
So if m larger than n by the pigeonhole theorem that we talked about last time, then there should contain one box. There at least there at least one box that contains more than one ball, but it doesn't matter here. So actually, in this question, we use a ball and stick method. So we consider there are m minus one stick, ball and stick method. So m ball, okay. So what you need to do is line up these m balls and then m minus one sticks on a line. So then you have the m plus m minus 1 factorial choices. But because the balls are identical, so it doesn't matter the order of the balls. So you need to divide by n factorial. And then the order of the stick does not matter also. So you need to divide by n minus 1 factorial. Then that's your answer. See if you understand this one. Yes?
Wait.
Understand? No? Yes, no?
Wait. I understand the numerator, now I'm trying to understand the denominator.
So it doesn't let's simplify the case, okay? Let's consider 2 ball and then 3 stick. So let's say if one of the drawings like this one, or some other drawing can be look like this one. So it means that if in this case it means that the fourth box contains 2 balls. Okay. This one means the first box, the third box. Okay. And then the order of the stick does not matter. So you need to divide by the n minus 1 factorial. And then the order of the ball does not matter also because the ball are identical. So you need to divide by n factorial.
Wait, so what's the answer for like the 5 ball, 9 boxes one?
So you just substitute n equal 5 and then n equal
Oh,
5, something like that. Okay. You just need to substitute that value. Then you can get the answer. So if like that in like that case, it should be 13 factorial divided by 5 factorial divided by 8 factorial. No question. No question.
No question.
No question. Then let's go back to the number theory.
Wait, but sir, wait. Why do we like? Why are we considering them like the same? Like, why don't we multiply like m factorial times n minus 1 factorial?
Because the order of the ball doesn't matter. Whether it is, no matter what is the position of the ball, okay? This ball like, we label it as AB or the BA, okay? It doesn't matter.
Okay.
So you need to divide by 2 factorial.
Okay, sir. And when do we know when to multiply and when do we know when to add like the factorials and combination?
And you need to do more questions to
Okay.
whether you understand. Yeah.
Okay.
So you save the screen, okay? And then let's go on to talk about the number theory. Actually, we have talked about, we have, you have learned more than enough in combination. So let's go back to the number theory. So the last time I think I teach you how to find the GCD of two large number. So then let's go on to talk about, we skip this part, we skip this one, extended Euclidean algorithm. So, and also, let's have a look at, hmm? I think it doesn't matter. So let's say have a look at other bases. The number that we use daily life in base 10, okay? And then let's say if, let's have a base 7. So you know how to convert it into base 10.
Yeah.
So, and then we can skip this one first. The combination have a lot of question about changing about the number in different bases. So we may need to have a look at this one. It doesn't tell you anything, okay? So let's go on to about the Fermat and this number. Oh shit. Oh, let's go, okay. Uh, the most common function look like this one, okay? The prime of this form appear in. Many people have thought that this is always prime if n is prime, but seem to have been first people to realize this one. But they're so dumb because they didn't check even for the prime number 11, okay? Do you know what this means? So it means that initially they think that 2 to the power n minus 1 is a prime number if n is a prime number. But even for n equal to 11, it is not a prime number. Factorization. So this number, we call this m number. I don't know how to pronounce this one, of course. So da 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 da. So it say that if n is a composite number, then 2 to the power n minus 1 is also composite. And then you may need to know how to factorize this one. So let's see, okay, let's have a look at this statement. So you may need to copy it down, okay? So we call it from this, how to factorize this one. Now, I think you know, obviously that this one has a factor, that is x minus 1. Because by the remainder theorem, for a function x to the power k minus 1, you know f1 is 0. That means that x minus 1 is a factor. And then by doing the long division, actually you can see it can be expressed as x minus 1 times this factor. Okay. Then, so what happens if you put x equal to 2? So you get 1 here, okay? So you get this one. Okay. Okay. So, and then you can see that if x is a composite number, if x is a composite number, if the k or the n is composite number, then it can be expressed as a times b. So you just substitute that number here, okay? And then you consider x to be 2 to the power a and k to be b. Can you see how to transform this formula to this one?
Yeah.
Okay.
मैंने उसको देखा था जब मैं उसके घर जाती थी तो वो सब कहती थी कि इधर आओ ये देखो बच्चे ने पॉटी करी बच्चे की वो साफ करो
Now a does
कपड़े
not
चेंज करो
a does not equal to 1 because n is a composite number. You can always find a non-C find these two the multiple of two numbers that is greater than 1 in a composite number. Then 2 to the power a minus 1 does not equal to 1. And also it is an integer. So you can see this number can be expressed as the multiple of two integers. So that means this number is a composite also. Okay, this is a very clever and very beautiful proof for this theorem. Any question? No?
So why does 2 to the power of a minus 1 does not equal to 1?
Because a does not equal to 1 now.
Oh, okay.
Because the n is a composite number, you can express composite number by multiple of two factor, two integers, other than 1. This is definition of composite. Okay. If no question, and then you may need to read the textbook by yourself. Okay. If you, and then since this one, okay, no need to talk about this. Okay. And then so you can check by yourself. So for the prime number, but the others are not prime. So you say that the largest prime we know that is this one. I think they use a supercomputer to show it. But I think your computer cannot do this such large number. So it say that if n, so another one is if m greater than 1 is not a power of 2, then this is a composite. But the reverse of this statement may not be true. So what does it mean by the reverse of this statement? Or the reverse is if m greater than 1 is the power of 2, okay? then 2n plus 1 is a prime number. It may not be true. So let's have a look at this one. So I think the proof is so similar. So you can have a look. By yourself. Yeah. It may not be that useful in the computation, but you can take a look. And also, don't remember, don't forget, okay, to learn some C++ by yourself before we're talking about some programming, or we may just directly do the questions in the past paper. Maybe we just skip this one first, okay? You can read it by yourself. So let's have a look at some more interesting part. It may be too difficult right now. So let's go on to next chapter. This one does not matter, actually. Doesn't matter. This one doesn't matter also. Okay, so I think you know this one already, okay? Every integer greater than 1 can be uniquely written as a prime or a product of primes. And then every integer can be written as a product of prime numbers. I think we don't need to have a look at this one. And then this is a composition, proposition. So all the integers can be written as this form. Okay, 2, 3, 4, 2, 3, 5, and so on are the prime number. So we can skip this one. And then another time is least common multiplier, multiple. And then I think we don't need to talk about this. So let's go on to next chapter. Okay? Maybe you read it by yourself, okay? So so show that this is irrational. It's not that you rational root theorem. So you may need to read it by yourself. A Pythagoras triangle. So this is some pairs of the Pythagoras triangle. So you may take some time to repeat by yourself. It's not difficult to understand, but it may be interesting. The difference of squares are, I don't know what you want to, so you can have a look by yourself. Prime factorization of Factorial. This may be useful. So let's say if you want to check how many zeros does 30 factorial end with. So how will you do this kind of question? I think it will be likely appear in the question. So how will you do this question? So let's check how many factor of 5 in 30 factorial. Okay. So if there is a 10 here, that means there is it has a factor 2 times 5. So let's say 30 factorial. We know that 30, any number can be represented as the product of the all prime numbers to some order. So let's say it has the order like this one. Let's say n2, okay? Times 3 n3 times 5 n5 times and so on and so forth. Actually, this does not matter for the zero. The zero doesn't only matters about is these two. Only these two matters. So do you know about the answer? What is the answer in this question in terms of n2 and n5? Hello.
Wait, could you repeat? Like,
So you know the answer for the n, the number of zeros in 30 factorial in terms of n2 and n5.
and what is N2 and N5?
You express the 30 factorial in this form.
Oh, okay, okay.
What do you think about it? No, it is expressed as the product of the prime number to some order. As a theorem stated before, all the numbers can be expressed as the product of the prime numbers. So that's why I don't write the number 4 here. And I think you know that for every 10, every 0 behind these zeros, these zeros means 10, okay? If you take out 1 0, that means you multiple by 10 or you divide by 10. 10 is a factor of 2 times 5. So you look at these two numbers. So let's say if n5 is smaller than n2, then the number of zeros behind that should equal to n5. Any question? Any question?
Wait, how is that like number at the behind like N5?
So let's give you an easier example, 600, okay? So 600 can be written as the product of the fact of the prime number 2, 3, and 5 only. So what?
Yeah.
So it is 2 to the power 3 times 3 to the power 1 times 5 to the power 2. Okay?
Okay.
So how many zeros are there? There are only 2 zeros. Actually, 2, what does it 2 mean? It means the order in the 2 here, okay? The order of the 5.
Okay.
So let's give you another example. Let's say 500. So this is 125 times 4. So it's 2 to the power 2 times 5 to the power 3. Why there are 2 zeros? because it's 2. All the 0 in that the number end with for in each 0 means 10. That is a factor of 2 times 5. So you just need to look at the order of the 2 and order of the 5 only. Then you can.
Okay.
So if you can express a number like this one, the 0 that this number end with should be the minimum of n2 and n5. The smaller value of n2 and or n5. No question?
No question.
And then let's see how we can find the n2 and n5 in 30 factorial. So we need to have a look. So we need to check how. So you know if it is a multiple of 5, it should end at 0 or 5. Actually, you have not much choice. In this simple question, you can write down all the choices and count the number. Okay. So these are all the numbers that end with 5 or 0.
Yes.
So the answer should be 6. But why not 5? There are only, sorry, the answer should be 7. But why not 6? N2 should, now the n here should be, here should be 7. Okay? It should be 5 to the power 7. Now, although there are 6 numbers, I think it's so easy, okay? You know 25 is 5 times 5, okay? So how about 2 to power this number? But obviously, if the question is like that, this order should always be greater than this order because there are more factor of 2 in between. In between 1 to 30. Okay? So we don't need to find this number to check the answer. But let's go back to check this find this number later on. So how can we get, so we know that n2 is greater than 7. So that means that the answer should be 7. You can check the 0 here. So you can find that there are 7 zeros. Okay? So if no question, now for the question in the number theory, there actually not a different way to do it. So let's say how we can find the number of n2 in this question. How will you do it? So you try to do it. So yeah, so let's see how to do this question. So for the n2, it should be the number of the number of the number that is a factor of 2 or multiple of 2 plus number of the factor that is a multiple of 4 plus the number of factor that is multiple of 8 plus the number of factor that is multiple of 16. We don't need to check 32 because 30 factorials don't have a 32 there. So, and then the number of factor of 2 should be so easy. Just 30 divided by 2 is 15. Then the factor of 4, not that difficult. You just 30 divided by 4. You get 7.5. Of course, you don't put a, you just take 7. So 30 divided by 8 should be 3 point something. Divided by 16 should be 1. So the answer should be 26. Actually, do you understand why we do it like that?
But so wouldn't it be double counting few numbers?
Sorry?
Won't it be counting 2 numbers twice?
No. Now, the number of factor of 4, that means it contains 2 to power 2, 2 to power 3, 2 to power 4. Now, all the number of factor that all the multiple of 4 is also a multiple of 2. So we can't, why we don't 2 times 7? Because that 7 numbers are also contained in the 15 numbers already.
Yeah, that's what I'm saying. Like,
So
won't you be double counting or even like triple counting few numbers?
No. Because we have can't, let's say we have the number, let's say the number 4, okay? Number 4 is a factor of 2 and factor of 4. So you should count, in terms of n2, you should count it as it 2 in the n2, okay? You count it once here, you count it once here. So you don't double count.
Okay.
So the answer should be 26. Okay, you can capture the screen. Then I think this is so the question is just you may read the following questions, following chapters. So actually they mean actually they are talking about the same thing that we talk about. 26 here. So you do it like this. Oh, we don't need to talk about this one. Haha. Oh yeah, going so fast. Haha. And we don't need to. I think I don't need to teach you this one, the geometric series. You may need to have a look at this one. There are infinitely many primes. Because I think we have talked about this already. I'm not sure if you still remember or not. But I think they prove it in another way. Actually, the zeta function, Riemann zeta function has some very special properties, not like this one. It can be used to find the value of pi. Okay, then maybe I'll just talk. Maybe let's talk about this one. The proof in the textbook is so difficult to you. So let me prove it like this one. I don't want to prove this identity. Let me prove it like this one. So, and then how can we prove it? We want to show that 1 plus 1 over 2 plus 1 over 3 plus 1 over 4. Now, although the number becomes smaller and smaller and smaller, but if you take the sum, it is infinity. Unlike this identity, unlike this one, unlike this series. I think you know how to find the sum of this series, okay? Every number is divided by 2. The final answer is 2 actually. This series will give you an infinite number. Let's see how we can prove this series to be infinite. So what I need to do is write down more terms here first. Let me write some more terms. Okay. Then, okay, this term is 1/2, okay, no problem. So if we sum up these 4 terms, no, if we sum up these 2 terms, now 1/3 is greater than 1/4. So 1/3 plus 1/4 should greater than 1/4 times 2, okay? That means this term should be greater than 1/2. No problem. And then if you grouping these 4 terms, then each term is greater or equal to 1 over 8. That means the sum should be greater than 1 over 8 times 4. That means it's greater than 1/2. Okay? And then you take the next terms up to 1 over 16. It contains 8 terms. And each term is greater than or equal to 1 over 16 times 8. So that means greater than 1/2. So you do the similar grouping and so on so far. Then what you get, this term should be greater than 1 plus 1/2 times so many terms. Actually, there are infinitely many terms. So this number should be infinity. Okay, that's what we call it diverge in mathematics. Any question here?
No.
So if no question, so we end the lesson today here. And then next time then we will go on to talk about let me see. So next time then we will go on to talk about chapter 6. We definitely need to learn these definitions and also some interesting theorem. So and then see you next Tuesday. Okay, see you next Tuesday. Oh no, see you on Friday.
Yep.
And you can have a look at this textbook. Yeah, you really take some time to look at this textbook.
Yeah. All right.
Yeah.
Bye, Mr. Young.
Bye.
Bye bye.
Bye, sir.
Bye bye.